Welcome back to the next session of this YM course titled Cornerstone Ideas in Material Science and Engineering. This is a quick recap of what we have done as far as the pedagogy and the content is concerned in the last few sessions. So, in the last few sessions, we looked at something called semantic maps, and we took specific examples to demonstrate what mind maps and concept maps look like. In fact, the last session, if you recall, involved a student activity wherein students came together in order to put a spider map or a concept map that established the various categories, the various kinds of information that they had learned, the properties and the connectivities. And as a consequence, it was an activity that was done together. It certainly, as you could have seen, enabled the students to think about the information that they had gathered in a rather new perspective. And there was a context to what they had studied. And another thing that we did discuss in the last class was about instructional scaffolding. And we have looked at scaffolding in the context of what is called as the zone of proximal development. And here it basically is a tool by which you can guide your students, provide a framework to your students so that you maximize the zone of proximal development. Another way of thinking about it is without the aid and with aid. If there is a substantial difference in the learning outcomes, that would be the ideal outcome of a teaching learning exercise. And using suitable scaffolding, hand-holding, guidelines, pointers make a very big difference to the learner as far as benchmarking their own learning activities is concerned. And we also looked at Bloom's taxonomy. And last to last session, you saw that there was a create level question that was actually given, wherein students were asked to draw the parallel between, let us say, vapor-based refrigeration and magnetic refrigeration. And they independently came up with the idea that in principle magnetic materials could be used as refrigerants. So you can pitch questions at various levels based on what you want the students to learn. And one of the responsibilities that the educators have is to, number one, ask this question at the outset, that is learning outcomes. What is exactly that we want our students to learn? What is it that we set in place so that they learn and they are responsible, they are given the responsibility of their education? What is the environment that we actually provide for them to learn? And finally, how do we evaluate the outcomes that we expect of our students? So this is really, I hope, a sufficient recap of what we have been discussing as far as the pedagogy is concerned. As far as the content is concerned, I will just show the concept map that the students drew by themselves by the end of last class. So you can see that students were able to sort of see that solids can be distinguished between amorphous and crystalline objects. Now what distinguishes between the two is ordering. So they use ordering as a functional term there. So this is putting things in context. So this is not so ordered, this is ordered. However, they did mention by themselves that here there is short range order that is possible. Here you have both short as well as long range order. And then they were able to distinguish between various crystalline objects, the possible crystalline objects. They called it crystal systems and Bravais lattices. They also mentioned that there could be 7 possible crystal systems. We came to this by using a brick exercise in the last class. And likewise, we also mentioned about the 14 Bravais lattices. And as far as crystalline objects are concerned, they also made a distinction between polycrystalline and single crystalline materials. And they mentioned that there is a transformation between the two possible through crystallization, recrystallization, grain growth, and so on and so on. So this is rather interesting because here they mentioned that there is a single crystal, here they mentioned that there is grain boundary, and here there is no grain boundary because it's single crystal. So they were able to understand the concept of grain boundary as put in this particular context. Furthermore, they were able to connect atomic bonding to bonding in solids. And they were able to sort of see that electronic configuration plays an important role in the role that the atom plays within the solid. And that is what they thought was the connectivity between atoms and solids through bonding. They mentioned that one could rationalize bonding by using either BACPR or molecular orbital theory. And they made a distinction between different kinds of bonding, namely covalent, ionic, metallic, and van der Waals. So they were able to put it together in the form of a connected map, in the form of a tree diagram, and it sort of tells you what the students are thinking. And exercises like this as a consequence can be very helpful for both the teacher as well as the taught. For the teacher to see where the students are, for the taught to see how and in what context the concepts that they are taught fit in. So we will continue with today's lecture. Today there are two things I want to talk about, especially in the context of pedagogy. The first one is what is called as inquiry-based learning. In some circles, it's also called Socratic learning. So it is learning that is enabled by questioning. So the teacher asks questions and asks the students to come up with answers. So you elicit answers from students. So there is a real engagement as opposed to the teacher teaching. The teacher asks the right set of questions, and these questions are oriented towards certain learning outcomes. So that's basically what inquiry-based learning is. And another concept which is very critical in our education system, and that is called inclusive education. So let me show what I have written about inclusive education. So this is how I have defined inclusive education. So inclusive education is one wherein everyone present learns through participation and a feeling of belongingness. Now this is very important. There's a lot of evidence that students learn best when they feel like they belong to the educational setting. So everyone, regardless of who they are, regardless of the, let's say, their cultural background, gender, identities of various sorts, physical or cognitive abilities, are welcome to contribute actively in a classroom setting. So such an educational environment would be considered inclusive educational setting. So as should be pretty obvious to those of us who are educators, inclusive education would obviously promote greater collaboration, greater participatory learning. Participatory learning is another word that I have introduced as a part of this particular course, and it's likely to offer the nucleus for social cohesion. So students who have exposure to an inclusive educational setting are naturally likely to accommodate others in their own life, and as a consequence, there's likely to be social cohesion. You are laying the foundations for social cohesion in the classroom, and an appreciation of diversity. The fact that we are all different becomes more clear to this learner who comes from an inclusive educational setting. So inclusive education settings appreciate the diversity of goals, aptitudes the learners bring to the table as well. So the teacher, for example, and all the learners, the participants in a classroom, tend to appreciate what others bring to the table, regardless of who they are, where they come from, what their current skill sets might be, and so on, because everybody is a collaborator in such a classroom setting. So this enables skill acquisition among all learners, and this is critical, and this is very important for a country like ours, wherein skill gaps are considered quite substantial, and hence fundamentally aimed at human development of the student and eventual social development. So having an inclusive educational setting is very fundamental to national building. Having said that, both me and other people have observed barriers to inclusive education that include sometimes attitudes of teachers and fellow learners. So when you have, let us say, a classroom where most learners are not sensitized, there may not be an inclusion. Similarly, teachers might be sometimes underprepared or overwhelmed. They may not necessarily understand the importance of inclusive education. So all these things can be barriers to inclusive education. Physical barriers, most obviously for people who are physically challenged in one form or the other. So how do we provide a physical space that is accessible? And curricular stress. So in many of our universities and schools, the emphasis is on syllabus completion. It is very little on student participation in the process. And this is a substantial source of stress for teachers as well. And this can completely disrupt inclusive practices. Similarly, under-preparation of teachers is something I've already mentioned. Poverty, socio-economic constraints, again a reality in our country. Administrative or policy inertia. So let us say that the teachers and students believe in an inclusive setting, but if administratively it is not supported or policy-wise it's not supported, it still would be an uphill task for the educators and the learners. So a spirit of collegiality is rather important to promote inclusive attitudes among students and teachers. Let me just correct the spelling of collegiality. So this is really what I wanted to say. Here in IIT Madras, in the Teaching Learning Center, I conducted a FDP on inclusive education, wherein there were a number of questions that were asked about students coming from various backgrounds, challenges they experienced, and so on and so on. So of course, within the course, this particular course, I wouldn't be able to discuss or even archive all that experience. But I just wanted to bring this out because this is a reality in our classroom settings and something that I think both teachers as well as taught need to keep in mind. So with that as, let us say, the pedagogical backbone, we will have examples of inquiry-based learning today in today's session. And what we will inquire about, that means what we'll ask questions on, would be the following. That is, we'll continue to ask questions on bonding structure correlations. Then we will look at some numbers that are very important. Alright, for example, if you talk about covalent bond, what is the energy associated with covalent bond? It is good for you to know. If you talk about van der Waals interaction, what are the energy levels corresponding to? What are the binding energies corresponding to? So when you understand these ballpark numbers, you get a better, firmer concept map in your head. Alright, and finally, we will try to deduce radius ratio rules by using drawings in your sheets, just like the way we deduced symmetries yesterday, and we deduced the fact that space filling requires certain specific geometries yesterday using diagrams. So today I will ask you to make some diagrams and we'll try to deduce some radius ratio rules. So that being said, we'll come to the questions for the day, because today we are going to do inquiry based learning. Okay, so this is the first question, and as I told you, you are all data enabled, so you're welcome to use your cell phones and so on to respond to these questions. In the past, in this particular course, we have used internet quite extensively to create tables, concept maps, and so on and so on. So we'll continue that tradition. So here the role would be, my role would be to ask questions and to elicit answers, elicit certain activities from the students. Okay. So the first question is there. What are the typical binding energies associated with covalent, ionic, van der Waals, and metallic bonds? So you can look at it in sequence. So open your data, discuss with one another. You can load share. For example, one of you could look for covalent, she could look for ionic, he could look for van der Waals. Then very quickly in 3/4 the time, in a fairly short period of time, you will be done with the data that you are looking for. So you will at least have data at hand. So why don't you write it down? So for a covalent bond, and there are multiple covalent bonds out there. So you can look at, let us say, a covalent bond that occurs in dash, some element. Which element can you choose? Just choose an element and give. So H2O is an example, but you have an OH bond, so it's not entirely covalent. It's covalent, partially covalent. But can you think of N2 would be an example of a covalent bond. Then can you think about another element that might have covalent bond? H2O2, O2. What about a semiconductor that is used for electronics? Silicon. Very good. So why don't you take a look at binding energies associated with each of these, because they will all be covalent. So do you understand this question? Yeah. So you can give me examples. So you can say my example for metallic bonding is for dash metal, and for that this is the energy. And remember, when you give energy, you should give it in the energy units. It has to be energy per mole or energy per bond, one of the two. So electron volts per bond. So are you making progress? Okay, very good. You're drawing molecules, but you'll have to show him also and tell him, so give him some numbers. Yeah. Okay. So I'll give you a very simple thumb rule which might be easy. Alright for you. So 96 kilojoules per mole is approximately 1 eV per bond or atom. Okay. So binding it. So you just use this conversion. So if you're getting in electron volts per atom or electron volts per bond, then you convert it into kilojoules per mole. You understand? So you just can use this conversion. I'll also do another calculation here. So this is also roughly 22 kilocalories per mole. You know how I did that. I just needed to divide this by 4.2. I would get this. So they're all equal. You understood? So if you're getting data in this quantity, convert it into this or this. But what is important is you should stick to one set of units. So in this table, what units would you choose? Okay. So these are like kilojoules per mole. So can you also give me numbers in kilojoules per mole? Or EV per bond, and you can use that conversion I have given there to go from electron volts per bond or atom to kilojoules per mole. So here, because I am asking for binding energy, it should be electron volts per bond. You understood? So you just have to do this. So it's very simple, isn't it? So if I have 2 electron volts per bond, let us say, I just multiply this by 2. It's very straightforward. You understand that, right? Yeah. You can give in electron volts per bond and then you convert it into kilojoules per mole. That's simple, no? You just have to use your calculator for that. You can then share. So what are the numbers you have found? Why don't you tell? Okay, why don't you show both the tables? You have already found a table. So you can take some representative values for metals, some representative values for gold and silvers. Yes?
For metallic bond, you are getting the length.
What is that?
This is for silver.
Silver. Okay, silver. That's for all right. That is the distance.
Yeah.
But
So
what about the?
convert the energy?
Yeah.
Sir, you are asking about the bond strength.
That is the binding energy.
The binding energy is not exactly the same because it's bond strength is how the balance electrons are bonded. Binding energy for every shell of electrons to be different.
Okay, so you're talking about electronic binding energy. I'm not talking about that. I'm talking about the following. So if I have atoms that are sitting together, if I have to remove this, what is the energy that I require? So let us say that I have just these 2 atoms. I have to remove this. What's the energy that is required? So it's binding energy per atom. As you pointed out, if you are looking at electronic binding energy, that means something different. That's okay. That is very important for spectroscopy. That's not what I was talking about. I'm talking about bond energy. So depending on the literature you use, it's so for example, if you look at some literature, the binding energy is an accepted nomenclature. But I understand what you are talking about. Yes, some numbers, please. Metallic bond, you are not getting that. Do you have metallic bond? Some representative values for metallic bonds. Around 200 kilojoules. So it's about 2 to 3 is normal. That is right. So let me make a table here. Or can one of you come and make the table and then you can ask, because now people have done some survey, there is some data available. So Vandra, can you go to the board? So you can write the type of bond and then the energies, whatever you get from this discussion. So you can give him numbers. So to begin with, you can write metallic, right?
You can begin with covalent also.
Yeah, you can begin with covalent. Okay, fine.
We have got for covalent, we wanted silicon.
Where will you get that kind of energy from?
Covalent bond or what?
Covalent will be less.
Huh?
It will be less.
Yeah, but the numbers are totally off.
Covalent bond.
So you can take a look at it again.
The carbon was
Yeah, please.
3.6.
So either the unit is wrong or the number is wrong. One of the two.
Everything in electron volt or electron volt. You just write electron volt, that will tell you. 3.6 kilo per carbon.
Yes. Yeah, how much? For carbon single bond, how much did you get?
3.6 electron.
Correct. That is reasonable. 3.6 electron volts for covalent, that's about reasonable. So in the ballpark of 4 electron volts, I would expect. So anywhere between 3 to 6, even 7 electron volts expected. Okay. So this is, so by and large the range here you can write is about 2 to 7. Alright. Now let's look at ionic bonds.
7.97 electron volt for sodium chloride.
Correct.
7.97.
That's right.
Electron volt.
So electron volts. Very good. And per bond, right? So electron. So here you can say per bond. Otherwise it's not clear. Whether you are talking about 1 bond, 2 bonds, 3 bonds, right? Very nice. Okay. So since you mentioned the unit here, EV per bond, we don't need to repeat this anymore because that would be redundancy. Right? So you can eliminate that. You can eliminate that because you have mentioned the unit here. So,
Madras.
for another ionic compound, So can you tell me the example of another ionic compound for which you got some data? Sodium chloride you have already given, 7.97 electron volts per bond, that's already written there. So actually, what I am finding is you probably do not know how to distinguish an ionic bond from a covalent bond. So there is a very simple thumb rule I will give you, which you can use. Okay, so there is a quantity called the Pauling's electronegativity. Okay, so there is a quantity. So it's called Pauling's electronegativity. Okay, so you will find data on Pauling's electronegativity for any given atom. Alright. So if I have two atoms A and B, and I let us say look at the Pauling's electronegativity of A, look up the electronegativity of B. If the difference is greater than 1.7, it's very strongly ionic. Okay, so that is by and large the thumb rule. Okay, so with that as the thumb rule, whenever you are in doubt, whenever you are not sure what kind of bond exists in the system that you are looking at, you have, let us say, some combination of A and B for which you have a table, but you are not sure whether you should put it in this category or this category. That's the challenge you are facing. Correct? So all you need to do is just take a look at the Pauling's electronegativity differences between those atoms, and then you should be able to find. So let me give you another example. Let's say potassium chloride. That's also a highly ionic system. Alright, did you find any number associated with that? The potassium bromide. Yeah. How much?
For potassium bromide.
Okay. Potassium bromide is ionic. Yes, I agree.
682 kilojoule per mole.
How? 682
kilojoule.
682 kilojoules per mole. So that is more like 7 electron volts per.
Yes.
Okay. So that's about right. So ionic bonds typically would have 4 to 9 eV per bond. So 4 to 9 eV. This is very, very common. Okay. What about metallic systems? Did you take a look at binding or bond energies?
Bond energies I'm searching, but most of the articles are not giving a specific value actually.
You should be able to find. So you, let us say, type out the keyword. The keyword in this particular case would be bond energy plus iron, bond energy plus aluminum, bond energy plus. Just do that. Yeah, just do that. So if you say bond energy plus ionic, it might not come out. But if you say bond energy plus aluminum, bond energy plus this, bond energy plus that, you might get some data. Copper is how much? That's correct. That's correct. So how will you so 176. So how will you convert that to electron volts per bond? How much is it?
1.8.
That's about right. So metallic, you're getting 1.8. That's for copper. Let's look at some more numbers. Instead of copper, can you look at, let's say, iron, aluminum? Very good. So van der Waals is about 10 milli-electron volts. So very small. No? So van der Waals.
So the
75.
So it's between 0.01 to 0.1 typically, van der Waals. Okay, so that's right.
the bond energy of gaseous diatomic iron species is given to be 75 plus or minus 70 kilojoule per mole. This is gaseous.
But then if it's not a dimer, it doesn't make much sense, right? Because you are looking for bond energy. So
It's dimer.
For bond energy of metallic bond in solid state.
yeah, and I mean, why don't you take a look at keywords? Punch in the keywords. That's right. So that seems very right, very reasonable. So 2.33. Something else? Gold is AU. Okay. Let's say silver. So why don't you just look for bond energy plus silver? So that's also right. So that's also a little lower than 2 EV per bond, right? And this is actually true for metals. So
Platinum it is 400. Platinum it is
yes. Platinum, tungsten, molybdenum, etc. would have very high. So, but the max it reaches typically is 3.8 to 4. So 1.5 to about 3.5 EV per bond is what you typically expect for metals.
Alright. In some metallic system, they will say that the bonding nature is not purely metallic.
Yes, so for example, tellurium. Tellurium is not really a metal, it's a metalloid. Okay, so it is not entirely like a metal. It's not a nucleus that's surrounded by an electron sea. There's also sufficient sharing of electrons between the neighboring atoms, and then there is a certain degree of covalency. This is right. I'm glad you brought this up because there are many systems, many examples, more examples of mixed bonding than of pure bonding. There are many more examples of mixed bonding. In fact, even in the last class, Bodhi had mentioned, about covalency versus ionicity. So you cannot necessarily look at an ionic solid and say it is perfectly ionic. It doesn't make sense. In fact, there will always be a certain degree of covalency as well. For instance, sodium chloride is highly ionic, no question about it. Highly ionic, no question about it. But you cannot sort of say that there is absolutely no sharing of electrons. So it's a question of degree. It's a question of degree. Yes, it is just a question of degree. That is why I said, see, this is a very soft criteria. If I look at Pauling's electronegativity, and if I find that the electronegativity difference modulus is greater than or equals to 1.7, it belongs to this category. But let us say that it is around 1.2, 1.3, then it has some mix of perhaps this and this, or some mix of this and certainly some mix of this and this. You understand? So that's a good question. Yes. Alright. So let us come to the next question. So one of you can take the picture of that because you work very hard on getting that data. So you can take a picture and share it to others in the class. And you have also learnt a criteria for determining whether or not something would be ionic, right? Good. Okay, next. Would bonding be contributing to the ability of metals to be ductile and malleable? So you have seen that there is some binding energy. Okay, it's typically in this window. And we have discussed earlier in this class that metals are malleable and ductile. You can draw them into sheets or you can draw them into wires. So would bonding be contributing to that? Or it's a completely independent feature? Why don't you discuss with one another? You understand the question? Are you making progress? What is it that you think about the question? Definitely contributing, isn't it? Okay. So metallic bonding versus covalent bonding, which one is directional? Covalent. So in fact, in the last class when you were using molecular orbital theory, you actually showed where that directionality also comes from. Right? So if you have something that is very directional, let us say I have a bunch of atoms, I have a bunch of objects that are very directionally sitting with respect. So these are all different objects, of course, but they are directionally sitting with respect to one another. Now, if I wanted to move, there is an enormous cost associated with it. But if it is a metallic system, is the metallic bonding directional or not? It is not directional, which means they can roll past one another. They can slip past one another, isn't it? So clearly, plastic deformation is made possible in metals primarily because these atoms are able to roll past one another, slide past one another. I heard some of you use the word dislocation. That is true, but we have not gotten there yet. So in principle, we can actually see, we can rationalize that the nature of bonding does influence properties. Okay, in this particular case, the atomic flow in the material, when you are subjecting it to a certain stress, whether or not atoms would be able to roll past one another, flow past one another would depend upon the nature of bonding. It's very clear. If it is covalently bonded to one another, they are actually anchored to one another. So for it to flow past one another would be difficult. But if it's metallic bonding, it's like a bunch of balls that are actually moving around. You can shove one over another and with little or no penalty. Some penalty, but it's very minimal. Right? You understand this? Okay, so that's absolutely right. So the nature of bonding does influence properties. And in the last class, I also showed you some data of silicon carbide, gallium nitride, etc. Did you notice that the band gaps are very different? And there is a very interesting relationship that exists between electronegativity differences, I have written here, and band gaps, the way I showed you in the data. But I don't want you to know that relationship, but I want you to understand that just like in this particular case, mechanical behavior, plastic deformation is related to the nature of bonding. In a very similar manner and in perfectly analogous manner, electrical band gap optical band gaps, those things also depend on bonding. So bonding is something very fundamental to material science. It's a very, very important starting point, one of the cornerstone ideas of material science. So why don't you Google this or use any of your favorite search engines? The word is allotropy. The word is allotropy, and come up with a formal definition for me. So, no, you'll have to search. And give me the formal definition. That's important. Formal definition. Okay? Because I also know something about it, but I want to learn the formal definition. Now, I'll give you an example of an allotrope, and let us look at the distinctions as far as bonding is concerned and structure is concerned. Let us compare graphite and diamond. Okay? So, let us compare graphite with diamond. So, why don't you look at number one, the nature of bonding in graphite, the nature of bonding in diamond, the structure of graphite and the structure of diamond, and let us see why they are allotropes. Okay? You understand? So, you will give me two data points at least, or two information points. One is, what is the structure of graphite vis-a-vis structure of diamond? Draw it and show me. Number two, what is the nature of bonding in graphite? You can give me the bond energy of graphite and the nature of bonding in diamond, and give me the bond energy. Okay, and let us compare the two. Because you have already studied bond energy, let us use that information. Are you able to get the data? So, structure, bonding, bond energy. Alright. So, can one of you volunteer? Bodhi, can you just draw the structure? Diamond versus graphite. You must have seen that, right? So, you can do structure, and then another person can come here and do bonding. So, I didn't. So, do you want to show where carbon atoms are?
Yeah.
So maybe you can put a ball. So just like the ball and stick diagram. Okay. So the sticks are bonds. The balls are atoms. Very nice. Good. And for the purpose of simplicity, because each of these will also be extended, right? Yeah. So for the purpose of simplicity, just draw the repeat unit. So in this particular case, this is what is repeated, right? So you can actually eliminate this. So for the purpose of simplicity, what I do is I just eliminate this, because what you have drawn here is actually true everywhere. So every atom is equivalent, right? It's a crystal. So this particular unit is going to be translated in all directions. That's what you are saying. Fine, very good. So are these hexagons perfectly similar to one another or different?
Average bond length will be same.
No, that's all right. But my question is this going to be same as this, or is this going to be different from this? It will be same. Okay, fine. As long as you are clear about it, it's okay. Keep going. Alright. Very good.
So this pi bond will be like
okay, very nice. So there is some pi bond, you say
localization of pi bonds.
Very nice.
So and next layer next layer will come.
Do you want to show how that layer will be structured below this? Will it be offset in some manner or some such?
Yeah, some step will maintain some idea.
So can you show that distance? And let's put some numbers. Have you seen some numbers? Let's say this is carbon, he says this is carbon. So what is the carbon-carbon distance in diamond? Can you take a look at it?
That is single bond. 1.5.
So it's 1.54 angstroms. So do you want to come and add to his diagram? So can you just write 1.54 angstroms here? And what is the carbon-carbon distance here?
1.45.
Ah, very good. So here the carbon-carbon distance is less, isn't it?
Yeah.
It's interesting. Now let us look at the carbon-carbon distance in this, between the planes. So here he has shown one plane. So the carbon-carbon distance in this plane is 1.4 angstroms. Now between the planes, what is the distance? Do you expect it to be more than 1.4, less than 1.4? More than 1.4. Okay, so now let us see whether it is twice, thrice, how much would it be? Okay, so alright, and the nature of bonding here and the nature of bonding here?
Yeah, both are covalent, but this will be hybridization will be different.
So last time you did mention about hybridization, so this will be sp3, there will be sp2, so you can write that down, sp3. And this is sp2, fair enough. And as far as covalency versus, as far as these identifiers are concerned, what about this, what about this?
Both are covalent.
Covalent, so you write that down also.
But in graphite, the interlayer is.
So just hold on. Okay, now what about this interplanar distance? Can you help me with that? Can you take a look?
3.35.
That's correct. Yeah. So it's about 3.4, 3.35 angstroms. That's right. So you see, here it's 1.4. So most covalent bonds are in the range of 1.5 angstroms. A max of let's say 1.82 angstroms. But here you have 3.35. It's none of these. So by elimination, it has to be van der Waals. So while here it is covalent, here it is van der Waals between the layers. So write it down. So here it is van der Waals. You understood? So van der Waals interactions can be much more long range. So they are truly long range interactions. Alright, and the average bond length in all of these cases would be in the range 1.2 to 2.3 angstroms in all of these cases. But look at the distance here, it's really huge. So it has to be something truly long range, and that is the van der Waals interaction. And now let us interpret this. What is the energy associated with van der Waals? It's an order of or two smaller than this, isn't it? So between them, the binding is much weaker than the binding in this direction. So you can lift this off in principle, because look at the energy, it's very small. The energy that binds this layer to this layer is very small. So in principle, I can provide that energy and it would be exfoliated. I could get this out. I wouldn't be able to do that in plane. Pulling a carbon atom out from here is going to be very difficult. But getting this out should be very straightforward. It should be very straightforward. Did you see that? In fact, this is behind the invention of something called graphene. And graphene, you cannot make it if this was not enabled by this van der Waals interaction. You wouldn't be able to make it readily, especially through exfoliation, because in exfoliation, you are ripping this apart, you are taking this away, and the only name is that would have been, and the reason why that is possible is because it's enabled by these small binding energies, these van der Waals interactions between players. Now, what about the bond energy? So, carbon-carbon bond energy here, carbon-carbon bond energy here, but you have two different types of bonds, isn't it? You have a bond here, and then you have another carbon-carbon bond between these two. So you have two binding energies, not one. Do you understand that? So why don't you tell me the numbers?
So it's
Why don't you go and write, Bona? Please go to the board, add to the data that is there on the board.
1 milli-electron volt interlays,
Graphite interlayer.
It's just how much?
1 milli-electron.
Very small. Isn't it? So that is 0.001 electron volts. It's very small. So what is the weakest bond in this particular system? It is that interlayer bond, is it not? So that is the one that you can actually use to chip off this layer over this layer. And out comes something that is truly a low dimensional material. Okay, and what about in plane? Why don't you all look?
Yeah, that is
So when they are looking for
6.3.
that, when they are looking for how much is it?
6.36.
6.36. That's okay. Compare that with carbon here quickly.
3.6.
Here is 3.6, and here it is
6.36.
Can you just double check this number?
It will be lesser than, because this is not
Yeah,
purely
no.
double.
So double check.
In diamond, what is the bond energy?
That is correct. So please write down. That is correct. 3.6. That is correct. Now the other one, I am a little suspicious of the number you have got. So please check.
It will be lesser than this one, 3.6.
No, take a look at the number. Look at data. Let the data speak to you. We don't have to be opinionated about materials. We'll get data and then make judgments based on that.
So can van der Waals force be called a chemical bond like covalent metallic and iron?
Well, what is chemical bond? Chemical bond is primarily to do with the fact that there is some electron transfer between the atoms.
Transfer or sharing?
Sharing. So essentially, electronic interaction. Is there electronic interaction? And between these two layers, is there electronic interaction? Answer is absolutely yes.
Because ultimately everything is electromagnetic in origin, all the forces.
Correct. I agree.
So I have never been able to answer the question why van der Waals force is not treated as a chemical bond actually. Means they are called intermolecular forces rather than chemical bonds.
Yeah, because see, so your question is, can you consider this to be a chemical bond? That's your question.
Yeah.
So see, chemical bonds are to do with the fact that there is some charge transfer. There is some charge. That means to say that there is some charge transfer between this system and this and this and this. The fundamental origins of van der Waals interactions are something called random dispersion forces. Okay, and that's a little outside the scope of this discussion, but it simply means when these two systems are sitting together, remember you have an electron cloud here for all practical purposes. You have pi cloud here and you have a pi cloud here. Now you have two pi clouds that are seeing one another. Then whenever there is a fluctuation here, there is an image of the fluctuation here. You understand? So just like induction. So whenever there would be a fluctuation here, there would be a fluctuation, and this fluctuation would be good enough to keep it together. So here it is not really overlap integrals or overlap of electrons, direct overlap of electrons in the classical sense, the way it is for these three bonds. Here it has to do with the fact that the electronic fluctuations are correlated with one another. That is why they did not typically call it a chemical bond. That's the reason why it is called.
Annual generally interactions with water.
That is why it is actually called as a secondary bond. So while these are primary bonds, because there's real participation of electrons, here what is actually there is the participation of electron fluctuations. So it's actually, these are primary bonds while this one is called secondary bond. But that's a good question. Good. Yeah. So anything else?
The in plane of
4.9. That is 4.9.
In plane of
that energy envelope.
So here it is how much?
4.9.
That is correct. That's correct. 4.9 EV is correct. So in plane here it would be 4.9. So look at the difference, right? So in plane it is 4.9 EV and between the layers it is 0.001 EV. Look at the difference. It's truly 2 orders of magnitude different. Right? So taking this apart, is rather difficult. But taking this entire layer apart is certainly possible, right? That is certainly possible. That is neat. You understand? So wonderful, very good. So can you appreciate the fact that structure and bonding are correlated as a consequence? So here is another case where structure and bonding is correlated. The atoms are the same, but they are clearly bonded to one another very differently. And hence the properties are very different. So graphite has a band gap of 0 volts, electron volts. Can you take a look at the band gap of diamond, please? Take a look at it. So
5.4.
that's correct. So 5.47 and here it is 0. So you see, the nature of bonding determines so many things. Of course, the binding energies, but also physical properties. In this particular case, the energy gap. So it's the same carbon, but the way the carbon is bonded to one another is very different in these two systems. So this is a case study on allotropy. Okay. So allotropes are elemental systems, okay, that occur in different physical forms because their underlying structure, crystal structure and bonding differs. So this is really the formal definition of allotropes. So it's not sufficient to say that they have different physical forms. It is not sufficient to say elements exist in different physical forms. They exist in different physical forms with fundamentally different structures and natures of bonding. That's the complete formal definition of allotropes. Now, with that complete formal definition of allotropes, let us look at the next question. So, the next question is, can glasses exhibit allotropy? Discuss with one another. So, I am going to give you glasses, same composition, alright. Can you actually make different forms as defined in this particular case? Can glasses show allotropy? You understand the question? So, you understood what allotropy is? Now, with this definition of allotropy, the question is, can I make glasses that are allotropes? Am I allowed? Disallowed? Can you take another picture of this and share with the class? Allotropy case study. Diamond versus graphite. And this is, by the way, 1.54 angstroms. So, whenever you give numbers, it's important for you to give units also. Alright? So, for example, when we wrote band gap, I wrote it in electron volts. Binding energy or bond energy, it would be electron volt per bond. Okay, so here also it will be per bond. Here it would be per bond. So please get your units absolutely accurate. So here also it's electron volt per bond. Here it would be angstroms. How many of you know the radius of hydrogen atom? How much is it? 0.5? Yeah, so around 0.52 angstroms, and that's also called the Bohr radius. That's also called the Bohr radius. It's very good. So this is clearly 3 times the Bohr radius, isn't it? It's 3 times the Bohr radius, and this one is about 7 times the Bohr radius. You know, between 6 to 7 times, 6.5 times the Bohr radius. It's huge. This is more than twice this distance, you see. And this one is shorter. How many of you can come up, or why don't you discuss the following? This is 1.4, this is 1.54. Why should this be shorter than this?
Double bond.
So that somewhere between single and double bond. Yeah, between 2 carbon. Very good. So why do you think it is not possible? So first of all, the word allotrope refers to strictly elemental systems. So most glasses, and here I have not mentioned, but most glasses are not elemental. That's number 1. But you could actually have amorphous carbon, for example. And the question is, can you make amorphous carbon allotropic? But please note that in that case, structure is ill-defined. Because it might have short range order, but doesn't have long range order. And because of these 2 reasons, it is not possible for you to have allotropy with glassy systems or amorphous systems. So it has to do with these 2 constraints. You can in principle have, instead of those glassy, if I replace it with let's say another word, amorphous. So either ways, you will not be able to come up with this underlying structure, a well-defined underlying structure. And since you cannot come up with a well-defined underlying structure and hence a well-defined underlying bonding, it's just not possible for us to actually distinguish between 2 physical forms, structurally or in terms of bonding. And hence allotropy is ill-defined when it comes to glasses or amorphous solids. You all understand this? Okay, let's look at the next question, and it is just to get you to be a little alert. Look around and identify materials. It could be anything, materials that are making up the chair, the table, your cloth, whatever. It doesn't matter. You write it down and you write out what you think is the nature of bonding in that particular system. So at least 4 materials around you, so that you become a little aware of your environment also. And the fact that materials are all pervasive, they exist all around you. You could look down, look at the tile, you could look around, you could choose to sort of describe the materials that make up this chair, this table, anything, it doesn't matter. So a few materials, 2 to 4 materials. So we'll stop in about 30 seconds, so you can tell me the materials and what you think is the nature of bonding in that particular material. You could also imagine or learn about materials that have gone into your cell phone and sort of say, okay, this cell phone, this particular component is made up of this material and this is the kind of bonding that is there in it. Okay. You could choose to talk about the mic and you could say that anything, it doesn't matter. The mic is made up of such and such thing. Yeah. Alright, so let's make a small list. So Malay, can you go to the board and you can ask people what their list looks like. You can take your own list with you if you want. So what's the kind of bond that you expect in wood and why?
This is mainly made of carbon also. So this is carbon with covalent bond also exists.
So most of it is covalent, you think. Very good. Do you think there will be some ionic bond somewhere? Not at all?
If some
Yeah, there will be some proteins and so on. They will have carbon, nitrogen and things of that sort. So there will be some mixed bonding. So you can put covalent plus mixed. So that seems reasonable, right? So for example, if there is any amino acid that is there stuck inside the stuff, so clearly there will be some ionic bonding also. Okay, next.
then that foam, whatever plastic that is polymer.
Okay, right up. So polymers, covalent plus mix, yes. Many plastics are covalent plus something else. Alright, very good. So you have started appreciating the fact that there can be mixed bonding that is present in a material, right? So not just in solids like the one that you were describing yesterday, or potassium bromide and so on, but in the materials right around you there is mixed bonding. Okay, the world around you has a mixture of bonding. Alright? Yes. Do you want to help them out? Listen to them also. We'll listen to them. Metallic frames, alright. So metallic frames. So these are mostly what kind of metals? Certain steels. Yes. So steels typically have iron and carbon and a few other things. So it has to be metallic bonding. But if it has a lot of carbon in between, then what would happen? Yeah, so there could be some impurities in it that could be having some mixed metallic bonding. Huh? Okay, so what is cementite? Fe3C. So what's the kind of bonding that you think will be there in Fe3C?
That is also metallic only. So even
no, but remember, these distinctions are very hand-wavy distinctions, because I have already told you about this. So iron carbide, there will be sharing of electrons, but there will also be transfer of electrons. It has to be there. So the distinction is how much of ionicity. Okay, so the people have come up with definitions, but they are definitions. Not everybody agrees on the same ionicity scale and so on and so on. But what you said is right. By and large, people believe that they are having metallic bonding. But remember, as I have already told in the past, mixed bonding is a norm. You naturally expect mixed bonding. When you say something is very covalent or it's very metallic, it basically means it's predominantly metallic, predominantly covalent with a little bit of something else. Okay, but metallic seems reasonable. So covalent is not so right.
Even if carbon is present, it is present in the solid solution, not necessarily covalent bonds are being formed.
Yeah, it's a separate phase. No, but
covalent exists always. Whatever metal bond is the iron oxide or iron carbide, always covalent bond.
There will be some amount of covalency. That's his argument, and he's right. So it might be more ionic. Okay, but then you have to come up with a number. Then you have to say, okay, 100% ionic vis-a-vis 70% ionic. But then how do you come up with that percentage? So there are people who have actually come up with definitions of these ionicities based on those electronegativity differences. Alright, but there is no uniform definition that is actually available for percentage ionicity. But the textbook for this course actually contains the definition for percentage ionicity, one of the accepted definitions, and you are welcome to look at it. So there is this.
In phases like ferrite or austenite, in which carbon is present in iron as a solid solution, I don't think any covalent bond is formed between carbon. Only alloy, you can get only metallic bond because alloy can prepare at high temperature, their covalent bond.
No. His question is, okay, you have carbon, and this carbon is sitting in an ocean of iron atoms. Okay, what's the kind of bonding that exists between this carbon and iron in the background? That's your question.
Yeah.
Right? So, what are the kind of interactions that can exist between any two atoms? Yesterday we had a discussion regarding that. So, carbon has some orbitals.
The van der Waals is always present, right?
Van der Waals will be always present, but it is negligible when you are dealing with things that are very closely interacting with one another. Because you have seen it's 1 by 100th or lesser, 1 by 500th the energy associated with others. Now the question is, if I have carbon that is sitting in a matrix of metallic atoms, how is it that carbon is interacting with those metallic atoms? That's the question. So one of the ways to respond to this question would be, okay, what is the electronegativity of carbon? What is the electronegativity of these metal atoms that are sitting around carbon? Why don't you look at it? So look at electronegativity of carbon, look at electronegativity of iron, and think about whether it's likely to be ionic, covalent, metallic. What would be the kind of bonding that exists between these two? So I told you about Pauling's electronegativity. If the electronegativity difference is 1.7 or more, then you can be very confident that it is very predominantly ionic. Otherwise, it's always mixed. It's always mixed. Huh?
Iron is 1.8.
1.8 is the Pauling's electronegativity of iron. Very good. That's correct. And then what about carbon? 2.5. So what is the electronegativity difference? Only 0.7. Yes. So there will be some charge transfer, but it's not predominantly ionic. Okay. Now both of them have an electronegativity difference of as much as 0.8. So it can't be entirely metallic also. So it's metallic with a wee bit of covalency. Definitely. A wee bit of covalency. So that's what he meant when he said that there will always be some covalency. So for the sake of clarity, you just write metallic plus mixed. Mixed. Because the word mixed sort of captures that. Correct? Next. Anything else? Any other material that you saw around you?
I don't think we see a lot of materials which are completely ionic.
Yes, because you need a very high electronegativity difference for that kind of complete electron transfer to occur. So when you have some completely ionic system, that's like having a situation wherein there are two atoms, one atom completely donates its electron to the other. What's the possibility of that?
The most common kind of bonding, I think, is metallic. It will be covalent.
Yes, that is correct. But if you are looking at only elements, then metallic bonding is the more common, because most of the elements in the periodic table are metallic. Any other thing? So before we close this session, I would ask you to make a concept map. Okay. So what are the things we learned today? How do they connect with one another? So what are the keywords? How do they connect with one another? And you saw the connectors. There are arrows, there are connectors, there are connecting words. So keywords, arrows, connectors. How are they connected to one another? You understand? So why don't you spend some time on that? So as you are making that, I will summarize the pedagogical points. So to recapitulate the pedagogical points that we discussed today, we looked at enquiry-based learning, and we had a classroom session which was primarily determined by questions, followed by enabling the students to come up with answers by themselves, eliciting responses by themselves, and as a consequence engaging them in some critical thinking. And then we also discussed what inclusive education is. That in this setting, of course, couldn't be easily demonstrated or cannot be easily demonstrated, but it is very relevant, as I told you. And inclusive education, the philosophy of it is to include people from all walks of life and ensure that their learning outcomes, their learning goals, their objectives, their aptitudes, their orientations, and their sense of belongingness are all enhanced. Because there's a lot of evidence that all of these go a long way in determining the quality of education and the learning outcomes that you expect of the students. Now, we'll let the students make their concept map for the next couple of minutes, and with their concept maps we will end the class. So what are some of the keywords? Bonding. There's also structure somewhere, right? That's also a keyword. Do you agree? Bonding and structure. Bonding and structure. What are some of the keywords? Okay, covalent, metallic, and why don't you discuss with one another? You can take their inputs also. So what are connectors that you can discuss with here? So another thing that you would learn organically is it will not be just covalent, ionic, metallic, and hot walls as we discussed. You could have mixed. So you have mixed bonding. In many materials you can actually see examples of mixed bonding. Very good. You saw that the largest fraction of elements are metallic. You can actually do that. Pure ionicity is very, very rare, and it's a statistical parameter. So you studied it in the context of Pauling's electronegativity and electronegativity differences, right? So why don't you populate that? So how are you doing? Okay, very good. You put some So bond strengths, and you have ordered it in a particular manner. So typically ionic bonds are very strong, followed by covalent, followed by metallic, and finally followed by van der Waals. On an average, this is just a ballpark thing. There could always be some overlaps. So there are always some overlaps between this. Do you want to indicate mixed bonding somewhere? And you also look at numbers, isn't it? So you look at typical numbers. And it's a statistical thing. Ionicity is a very statistical thing, right? So you looked at it in the context of Pauling's electronegativity. So I'll tell you how you have to do. You have to do it in the form of some tree. So you have something and something else, and between them there is some connection. Then there is some property described here. Maybe some examples, things of that sort. So that there is a knowledge tree, and you see the connect. There may be some connect between this and this that you see, and so on. So there is a concept map. There is a headspace that you are creating for yourself. Allotropes, very good. So if you discuss with one another, you might actually come up with this one concept map per table case. So you can look at, let us say, the way she is drawing, and maybe add in there. So you can add in. So you can allow him to add in, allow him to add in. So you can also draw in his sheet, so that your inputs are also there. So feel free to draw. So let me see what you are at. Oh, very good. So you are able to connect ideas. Very nice. So elements, bonding, compound elements, allotropes. But then if you have compounds, then you can have ionic bonding, mixed bonding, covalency. Even in elements, covalency can be there. In elements, metallicity can also be there. So this is an interesting thing. So they have actually in their diagram shown that elements can be covalent, metallic, but not ionic. Makes sense, right? Correct? So can you represent that fact in your tree as well, please? You understand? And then most materials have mixed bond. So that's another thing that they have captured. So they have made this distinction between elements and compounds and common materials. You can pull out arrows, you can draw something here. All of that is allowed. Oh, very good. Properties. The fact that allotropes have different properties, bonding, structure, and hence, for example, in the case of carbon, in the case of diamond and graphite, different hybridizations even. Correct? And yes. Yes, very good. So bonding and properties are correlated, correct? So
structure also.
And structure and bonding are also correlated, right? So allotropic and okay, so you have put bonding on top. Okay, fine. Sure. And maybe you can put some numbers also somewhere there so that it registers in your mind. You can open up your cell phone, you have an image of numbers. So this is, so let's see. So, okay, you have chosen to put elements on top. Yeah. So how are you going to connect this and this?
Here you can add element. You can consider the bonding, the different type of bond will come. And the bond strength, you just put the arrow down, the bond strength will come. Again, element can be different allotrope, it can show different allotrope. The allotrope have different structure, hybridization, their property, and they have band gap, different band gap. And also element, they can bonding also different type of bonding overlap is there. Okay. But I'm trying to see how you can integrate your two clusters. So you have one cluster of ideas there, and then another cluster of ideas here, but you are not able to combine it. Why? Maybe you should put some thought into it. This is interesting. So you are able to combine things. You have chosen to have diagrams, drawing also as one 3 diagram. Okay. And you can put some bond lengths or bond strengths or whatever.
To the elements we come to know that.
Element different bonding is showing that a different metallic covalent ionic.
See, these properties, band gap, this, that, and so on, need not have to do with elements, because you could. Correct, I understand. So these allotropes can have different properties because they have different bonding and different structure. That's what you are claiming here. Fine. Now, and also allotropes could have mixed bonding also. You just saw, for example, between in that particular case, you have valence van der Waals interaction along with covalent. So that's also possible. Now, here you have mentioned types of bonding: covalent, ionic, metallic, van der Waals, etc., etc. Can you connect bonding structure and hence bring allotropes? Isn't it? Yeah. Because that is one thing that I discussed in the class. So that's part of the formal definition of allotropes. So bonding structures are both important. Okay? Yeah. And which is the weakest bond? Van der Waals, right? So what are the typical numbers associated with van der Waals? A few milli-electron volts. Yeah, very good. Okay, fine, very good. So that's a nice knowledge tree. So can I show you the others also? Okay, please. So do you want to work with that? Fantastic. Now you start populating here, and you can put some numbers also. So here itself you populate. So it becomes one concept map. So you're creating a headspace for yourself. That's the idea. So you see how concepts are connected to one another. There may be things connected here to something here. So you have to look at that also. Property, very good. So band gap is actually a property, correct? Fantastic. Then, so covalent bond is directional, you said. Metallic bonding is not directional, and we discussed that it has an influence on the property. For example, metals are malleable and ductile because of metallic bonding, right? Because of the non-directional nature of bonding. Wonderful. So let me show this. So you can just add that also, and then we will close this class.
So is a covalent bond stronger than ionic?
On an average, no, typical, see, you cannot say that directly, So because though we have put some number windows, remember all those windows have overlap. For example, in one case it is between 2 to 4, in another case it is between 2.5 to 5.5, something like that. So the specific case has to be looked at. You cannot make a generic statement that ionic bond will be naturally stronger, because as I told you, there is no genuinely, truly, completely 100% ionic bond in the world. Okay, and given this nature of it, these are pedagogical trends. These are helpful for classification in our mind. But when a case is given to you, you have to investigate what is the binding energy. Does it seem like it will have large delta EM and so on and so on. Okay, so with that, let me just show this if you don't mind. So this is the work of this group here. They have come up with concept map organisms. So this is how they understood what was taught in the class. You can see there is a lot that they see. So that is a good sign. And here. So maybe you can work on this as part of your homework also, add a little bit more, but this is also very nice. So you see how bonding and structure, allotropy, etc. come together. And of course there could be properties also that could have been introduced, some case studies that could have been introduced here. Okay, with that we come to the end of this session. Thank you very much.